Alright, hello everyone. Now let me take the lecture video for the final week of this spring semester. So what I'm going to do in this last video, I'm going to talk about, I'm going to address just one topic in chapter 13 of our textbook. Although there are many important topics in that chapter, let me just talk about Kuhn-Tucker Theorem. So I chose the most important one in that chapter. So Kuhn-Tucker Theorem tells us how to find a solution to optimization problems with inequality constraints. So in this last video, we are going to study inequality constraints. So you may wonder why we have to care about inequality constraints. So just for motivation, many economic models can be put as optimization with inequality constraints. So for a specific example, if we consider consumer's choice problem, the so-called utility maximization problem, so there is one consumer who attempts to maximize this utility, and utility function depends on x1 and x2, so the demand for good 1 and demand for good 2. Okay. And intuitively, if we think about the consumer's choice problem, there is a restriction on the possible choice for x1 and x2. For example, consumer cannot choose to consume, say, infinite units of good 1 or infinite units of good 2, unless these two goods are free, right? So the consumer will encounter budget constraint. So the budget constraint shows the possible choice for x1 and x2. So intuitively, her expenditure, so the consumer's expenditure on these two goods cannot exceed disposable income, right? So if we think about this budget constraint, once again, that shows the possible choice for x1 and x2, but there is no reason to insist that consumer spends all of her income. Okay? So she may choose, say, not to consume anything, so 0,0 for x1 and x2. That is also a possible choice. So that means this budget constraint should be given by inequality constraints rather than equality constraint. And the consumer's utility maximization problem is often regarded as the most standard optimization. So, even the standard problem has inequality constraint. So we should know how to deal with this. But unfortunately, the previous method for finding solution to optimization problems with equality constraints, so the Lagrangian multiplier method, does not work for inequality constraints. So we have to devise a new method, and then the new method appears on page number 8. So when it comes to these Kuhn-Tucker conditions, we have to check three different conditions. So if we come up with this optimization problem given inequality constraints, we have to check. So we first set up the Lagrangian and have to check the point is going to be a stationary point of the Lagrangian. I think we are now familiar with this condition, so that is not that different from the Lagrangian multiplier. And second, we have to check the point we look for, so the solution to this optimization problem satisfies the given constraint. That is also not surprising. But the third condition, complementary Slantness condition, that is kind of new, okay? So let me first elaborate on where this comes from and then show several examples to illustrate how this Kuntucker condition is applied to find the solution, okay? Probably I'm going to do that, so I'm going to show you examples in the next video, okay? So in this video, I'm going to focus on theory, okay? So as usual, I'm going to begin with the simplest case to develop ideas, okay? So here's one function we want to maximize. The function f depends on just one variable, and we'd like to maximize this function given this constraint. So x1 should be non-negative, okay? And let me denote by x1 star the solution to this optimization problem. Right? So if x1 star is the solution to this maximization problem, then, if this was the solution, then x1 star must obey this constraint. So x1 star must be larger than or equal to 0. Okay? So we have two possibilities. Solution may occur inside the region. So inside the region given by the constraint. So at some positive value, as depicted by the first figure. Okay, so we have an interior solution in this case. So the solution turns out to be strictly positive. In this case, this given constraint is irrelevant because we assume x1 is a non-negative, but turns out that solution is a strictly positive. Okay, so we say that constraint has slack in this case. Constraint has slack. Okay, in the sense that function is maximized at x1 star. So the given constraint requires x1 be non-negative. So we have this amount of slack. But the second case, so these two figures show the possibility of boundary solutions. So x1 star may be equal to 0. May be equal to 0 depending on the characteristic of the function we want to maximize. All right? So at the boundary solution, we have two different cases. So in part B, so in the second figure, the derivative, so the slope of the tangent line at this optimum point is equal to 0. But we should take this as a coincidence. In most cases, the derivative will be negative like this. Okay? So if the function is maximized in this region, so in this first quadrant where x1 is non-negative, then the slope of the tangent line at this maximum point should be negative. That means the function is monotone decreasing in this region. So the solution occurs at the boundary point. Okay, and in this case, we say that constraint is binding. Constraint is binding, or active. Constraint is active, or constraint is tight. All right, so depending on where we have a solution, this simple example demonstrates that we have different first-order conditions. Okay, so the optimization, maximization, or minimization condition for the solution. So if x1 star was the solution, interior solution, then f prime should be equal to 0. Okay, then the solution is strictly positive. But if we have a boundary solution, as in B and C, now the derivative is non-positive. So it may be equal to 0 as in B, but in most cases, derivative will be negative as in depicted by figure C. Okay? All right, so the main difference from the previous case, we had a unified first order condition for maximization or minimization. That was the derivative is equal to 0. But whenever we have this kind of inequality constraint, now the first order condition involves equality and inequality. Okay? So it may be either this or this, depending on where we have a solution. Right? But one important thing you can observe is in both cases, we have this common condition. Right? So if we multiply the derivative and the solution, no matter where we have a solution, that boils down to 0. Right? So this condition tells us at least one of either solution and the derivative must take a 0 value. And this is often referred to as the complementary Slantness condition in the sense that, so if x1 star was the solution, then this solution has to obey the given constraint, right? So originally we have this constraint on the solution, right? And if this was the solution, it has to obey the second constraint that comes from the first order condition. So f prime should be negative at this point. Should be non-positive. So either equal to 0 or strictly negative. Right? So optimality condition gives rise to another constraint on f prime, the derivative. Okay. And then this new condition, complementary Slantness condition, tells us if x1 prime is a strictly positive, okay, then the derivative automatically is equal to 0. Okay. Otherwise, this condition is not met. Okay? And vice versa, if f prime is strictly negative, then we must have the boundary solution. Okay? So, the reason for complementary slackness condition is if this constraint has slack, right? X1 star is strictly positive, and the other condition should be binding by this complementary slackness condition, right? Or if this constraint has slack, so f prime is strictly negative, the other constraint must be binding, right? So this condition shows that there is a complementarity between these two constraints, okay, in this sense. So this is why we call that complementary slackness condition, okay? And that is the basic idea of the third condition in the Kuntucker theorem. And if we slightly modify the constraint, now x1 is required to be larger than or equal to c, some arbitrary constant c. Still, we have two possibilities. So if we have an interior solution, the derivative must be 0 at that solution. But now the solution is strictly positive, strictly larger than c. If we have a boundary solution, now the derivative may be equal to 0 or smaller than 0. But now we have a boundary solution. Okay? So now the complementary slackness condition can be written as, no matter where we have a solution, the derivative, so the product of the derivative and x1 star minus c is going to be 0. So the condition can be written as x1 star minus c times f prime is always equal to 0. Okay? So to summarize our discussion, if the constraint has slack, meaning that if we have an interior solution, the optimization condition is identical with the unconstrained optimization condition. Okay? So f prime is equal to 0. So that is a standard first order condition. If we attempt to maximize this one in the absence of the constraint, we start by taking derivative and setting it equal to 0. Okay, so this was the standard first order condition. So if the constraint has slack, so if this constraint is not that important, so in the sense that solution is maximized, so the function is maximized x1 star strictly larger than c. Okay, in the sense that, so in this sense, when constraint is not that important, so whenever it has slack, optimization condition is the same as before. But when the constraint is binding, the condition becomes derivative is non-positive. Yeah? And in either case, the complementary slackness condition is satisfied. So our discussion tells us whenever we have this kind of inequality constraint, we have to divide our analysis into two cases depending on where we have a solution. Okay? And then we have to check whether complementary slackness condition is satisfied or not. But in fact, there is a very effective way to unify these two approaches. Okay? And that can be done by using the Lagrangian multiplier method. Right? So it turns out that the previous analysis, the previous method of finding a solution to optimization with equality constraint can be used to find the solution even in case of inequality constraints. Right? Now let me illustrate how to do that. Now going back to the previous example, we want to maximize function f given this constraint. And just as we did in case of equality constraint, we set up the Lagrangian. Right? But there are two important differences. The first important difference is so from the previous Lagrangian method. Now the multiplier is non-negative. Okay? So the sign of the multiplier is very important. Right? And the second, so we set up the Lagrangian as before. So we put the objective function first. and then plus the Lagrangian multiplier, and then multiply by the constraint. But now the way to convert this constraint, when we write the Lagrangian, we have to convert it to this form. So x1 minus c is larger than or equal to 0. Okay? So we should translate the given constraint to this form. Something is larger than or equal to 0. Right? That means if the inequality was reversed like this, and we change this to c minus x1 is larger than or equal to 0. Okay? And we put this form into the Lagrangian. Right? So I want to discuss why, but I have just a limited time. So you're going to study that why. So you're going to study why in the second sequence of the math econ, right? So in this last video, let me just focus on the method itself. All right, and then, but this sign of the multiplier, so the law of this sign of the multiplier will be clear in a second. Okay? So after setting up this Lagrangian, we take the derivative with respect to the choice variable, just as before, and set it equal to 0. Then the objective function becomes f prime, and lambda x1 becomes lambda. Okay, so we come up with this condition for a stationary point of the Lagrangian, right? Because we assume lambda is non-negative, and let me rewrite this to f prime is equal to negative lambda, but we assume lambda is non-negative, right? So this condition tells us f prime is going to be non-positive, okay? So if lambda is strictly positive, then the derivative will be negative, strictly negative. And if lambda is equal to 0, the derivative is going to be 0 as well. Right? But this is very simple. It's not surprising at all. But with this one condition, now we can express these two separate cases at the same time. Okay? So now, depending on lambda, we can make this first order condition by setting lambda equal to 0. Okay, and we also can produce this first order condition by setting lambda non-negative, right? So this familiar condition consolidates the two separate first order conditions previously into a single condition. Okay, and furthermore, the condition reveals one important relationship between the Lagrangian multiplier and the constraint. Okay? So previously, we write the complementary Slantness condition in terms of the constraint and the derivative, right? And then we can rewrite this to multiplier and the constraint. Okay? And because, if we take a look at, if we think about this case, if lambda is strictly positive, okay, then by this condition, f prime is going to be strictly negative. Right? But when you have this condition at the for the optimality condition at this solution, whenever we have a boundary solution, okay, so negative derivative at the solution means we have a boundary solution. So the solution must occur at the boundary. Right? And if conversely, if we have an interior solution, x1 star, now strictly larger than c, then we must have zero derivative at this interior solution, right? But if f prime is equal to 0, and by this condition, lambda must be equal to 0 as well. Right? That implies lambda is also equal to 0. Right? So previously, we set up the complementary Slantness condition using this relation, these two relation. Oh, sorry, this two relation. Right? But now we can express the complementary slackness in terms of lambda and the constraint. Okay. The one advantage of doing this is, we don't have to compute the derivative at the solution. Okay. So, we don't know where the solution occurs. So, if we compute whenever we have to compute this derivative, we have to figure out the derivative and the solution, right? There are two jobs we have to do, right? So that is really cumbersome. But by expressing the complementary slackness condition in terms of lambda and the constraint, we don't have to do these two jobs. Okay? So the corresponding complementary slackness is going to be lambda times x1 star minus c. That is always equal to 0. Okay? No matter where we have a solution. Okay? If lambda is a positive, x1 star is going to be c. So we have a boundary solution. So this equation, this expression comes down to 0. When you have an interior solution, now lambda is going to be 0. Okay? So once again, the product is going to be 0. All right, so now we are going to generalize this finding to a general problem. So the function with multiple choices. Okay, now the function depends on x1 and x2. And then constraint is given by a general form. Function g should be lower than or equal to c. Right? And suppose that x1 star and x2 star is a solution to this maximization problem. So now we divide our analysis depending on where we have a solution. So solution may occur inside the region, right? So we may have an interior solution, okay? Whenever we have an interior solution, the optimal condition, the optimization condition is the same as before, okay? So there are two partial derivatives in the absence of this constraint. The way to maximize this multivariable function, we take the partial derivatives and set them equal to 0, right? And then the same condition can be obtained by setting up the Lagrangian. L is x2 plus lambda. Remember, we have to change this constraint, this form, larger than or equal to 0. Okay. And think about lambda is equal to 0. Okay. Then this constraint term drops out of the Lagrangian. So now the Lagrangian just the same as the objective function we want to maximize. Okay. So the standard condition, the stationarity condition of Lagrangian. So I mean this condition, two partial derivatives are equal to 0. So this condition is the same as we have a stationary point of the Lagrangian. When lambda is equal to 0. So when lambda is equal to 0, there's a no difference between Lagrangian and the objective function. So this, standard condition captures the, the previous first order condition when we have interior solution. But when we have a boundary solution, now the constraint is binding at the optimum, so at the solution, right? Then, solving this optimization problem is essentially equivalent to solving this. So now the problem with the same optimization condition, but the constraint is now given by the equality. Okay, so solving the constraint optimization with equality is the same as the solving with inequality, right? Turns out that the solution to this optimization is a boundary solution. Solution occurs on the boundary. Okay. So we can initially set this constraint equal to each other. right? And solving the same problem, we are going to get the same solution, right? So just as we solved this equality constraint using Lagrangian, right? So the previous stationary condition will play a role of the first order condition. So we have this, right? And no matter where we have a solution, the following complementary Slantness condition must hold. All right. So in summary, inequality constraint brings us to new necessary conditions for a solution. So the Kuhn-Tucker condition provides us, some necessary condition for a solution. Okay. So if some x1 and x2 is a solution, the following Kuhn-Tucker conditions must be satisfied. Right? And the first condition requires so if x1 star and x2 star are the solution to this optimization problem with the inequality constraint, then x1 star and x2 star must be a stationary point of the Lagrangian. Okay, so that means partial derivative with respect to x1 and with respect to x2 should be equal to 0 at this solution. Once again, this is a necessary condition. First necessary condition, and the second necessary condition is the constraint must be satisfied. Okay? And finally, the complementary Slantness condition must be held. All right, so we have to check these three conditions. That is going to be the first step for finding a solution to constraint optimization in the presence of inequality. Okay? And it is very useful and instructive to compare this Kuntucker condition with the previous Lagrangian multiplier method. And remember, Lagrangian multiplier method was used to find a candidate for solution in the presence of equality constraint. This was used when we have equality constraint, and Kuhn-Tucker condition is used when we have an inequality constraint. Okay, and the previous Lagrangian multiplier method states that suppose that x1 star, x2 star are solution to this constraint optimization with equality. Then x1 star, x2 star, and lambda star, even lambda star, becomes a stationary point of this Lagrangian. Okay, that means partial of Lagrangian with respect to x1 and x2, and even with respect to lambda, these three are all equal to 0. Okay, but if you compare this condition with previous Kuhn-Tucker conditions, you may observe some differences, right? So first, a common thing is both methods use the same form of the Lagrangian, and both require these two things. So at least the derivative of the Lagrangian with respect to choice variables should be equal to 0. Okay. In case of equality constraint, so Lagrangian multiplier method requires these two are equal to 0. And in Kuntucker condition, the very first condition in Kuntucker theorem requires x1 star, x2 star should be a stationary point of the Lagrangian. So we have the same condition, and we have the same Lagrangian, right? But the difference is the third condition, okay? In Lagrangian multiplier method, the derivative of the Lagrangian, even with respect to Lagrangian multiplier, is equal to 0. But if we take the derivative of the Lagrangian with respect to lambda, we are going to have this one, the constraint, right? So the stationary point of the Lagrangian with respect to lambda requires the constraint must be binding. Okay? So that is true when we have equality constraint, right? But in case of inequality constraint, it may be binding or not, right? So this last condition in Lagrangian multiplier So now is replaced with these two conditions. Okay? So the constraint may be binding or may have slack. Right? But regardless, the complementary slantness condition must be satisfied. All right, and then one more important difference is, there is a no restriction on the sign of lambda. Okay, in case of equality constraint. Okay, so lambda can be positive or negative. In case of inequality constraint, lambda star must be non-negative. All right, then now I'm going to illustrate how this theorem is applied to several examples. Okay, so first let me stop the video. Let me stop the first video here, and in the next video, I'll continue to talk about Kuntucker theorem.